Okay, so we are now recording. Hi all. This is Mani. I am a data engineer. I have around 10 years of experience. I currently work at a cyber security company, and my primary role day-to-day job is uh, like ingesting a lot of data using Python, SQL, Snowflake, and providing data to the stakeholders. And I've been doing this around close to 8 years right now. Like it was called with different names back then, big data, ETL, whatever, whatever. So yeah, that's what I've been doing with my career. I started off as an automation tester. Now I'm here, after 10 years. So today we will be talking about data engineering, right? Um, what what what's data engineering? Um, why do we need it? And what's the future in it? All things data engineering. I hope you guys can see my screen. Can somebody like confirm this?
Yes.
Sorry, you can see
Yeah,
my
we
screen, right? It's on notes. Like,
Yes, we can see it.
okay, got it. So is it like my handwriting is like I have written this like on like like a pen and paper thing. Uh, it's like it's not too bad, right? Like you guys can like see it and understand it, right? I'll just explain everything, but I'm just trying to like get the feedback from you guys early on. Okay, so you can give me feedback on the chat. I'll just go ahead with this one. So basically, like whenever we think about data as an industry and data engineering as a discipline or a practice, we sort of gloss over a lot of important stuff. In my opinion, we kind of like um, have a simple notion that okay, you are bringing the data into a data warehouse and then serving it to people. That is fine, but let me just go for uh, simpler explanation as to what we do as data engineers and how what's our day to day work. And even before that, I'll just say ahead about data. What is data? Data is basically a collection of a fact or an event that happened. Let's say you went to a grocery store today and you said, I want to buy chocolates or I want to buy some groceries. So there will be some place where the teller or the person who is standing at the counter has to make the note of that particular event that is occurring and the facts, how much you paid, how much you bought, and are there any discounts. All of this information should be recorded in some kind of a ledger or some kind of a book, basically a record. So all these are all records, right? This is basically what in a simplest form is called a record, right? And in before digital era, it was all manual, it was all on books, and then we moved to digital era where we asked computers nicely to just store our data in certain format where we can do it. And then as internet start to happen, and we all started to like get things done through internet, and every interaction is being recorded, tracked, and used. So we have started collecting huge amounts of data, right? That was never happened before internet era, or at least it didn't happen at scale for every single company on the planet, right? So that's where this whole big data thing came in. Big data means really huge data, basically. That's the dumbest explanation that it could have. And how do we store that data? How do we like scale the systems that stores this data, and how do we process it? So all of these questions are answered in big data, right? And then what is data engineering? It's just a fancy name on top of big data technologies where you use um, like a cloud based data services, modern data storage, retrieval, and techniques, and scaling infra. All of this comes into data engineering, basically, right? So in simplest of explanations, this is what basically data, big data, and data engineering means, right? So now when you think about how these data systems evolved, right? We kind of have to go back into our history, basically history of digital era computing, data storages, and all of that, right? So before 1970s, there was this event happened where we launched human beings into space, and NASA did that, right? So the first data, massive data storage systems by that era's time was basically the Apollo mission, where they sent people to space or on moon. NASA wanted to like build a huge data storage system for the parts that are used in the rockets, basically, like around 9,000 parts, which vendors, what is the specification, how it is changing, all of the data need to be recorded, right? And how are we working, and the project data, everything need to be stored in some system. So that's when the first data storage system happened. At this time, the computers were, of the size of buildings, not a floor. The whole building was a computer. So it was in only in research institutes in US, and that's how it was, basically. So at around, after that, researchers in IBM, basically Edgar F. Cord, you might have remembered if you had, experience in data, you might have heard about, Cord, basically from Boyce Cord normal form, or BNF normal form. So the same person who has invented something called structured query language. It was different from other types of languages there, like hierarchical ones and all of that, where they used some form of programming or some form of a language structure to store and retrieve the data. So by 1980s, this got to a point where every single system who wanted, like every single company who wanted to have a data storage system, they opted for RDBMS because of its simplicity, because of its language being very like English like, and you don't have to remember a lot of stuff. Any normal person can just go ahead with RDBMS system, and then they were fine. Basically, they could store, retrieve, and process data however they want. As the data grew in these companies like NASA, or let's say steel companies, like commodity companies, all of these were like huge systems, right? At that time, at least in the US, where they said, okay, now we are storing the data in a database, that is fine, but we want to do some analytics on it. We want to see whether we have increased our sales year on year. How do you do that? DBs storing the data were good at storing the data, like doing small transactions. And if we run any large or long running tasks, like analysis, like whether the sales happened, sales grew or not, whether the particular product is doing well or not, these kind of analysis were not good in DB systems, because they used to take a lot of time, and we have to join a lot of tables, and if we have to basically process a lot of data. So that was not possible in DBs. We will understand about it a little further in the upcoming slides in the within this session today. So DBs were good at transactions. Like let's say I have placed an order. Okay, databases are really good at noting the transactions down, because that is small data, and plus unit operations means only one operation. Okay, either you create, update, okay, create, read, update, or delete. You do only these operations for the most part, right? So even delete, we will not delete the whole tables data. We will delete only atomic records, or one or two records, or only tens of records, very less number compared to our analysis systems. So this is what DBs were really good at. But we wanted to have large processing of data, because that's where our value is, right? So what they did was they created something called as a data warehouse system, which is really big in storing data, and also processing data. They called them as MPPs, or massive parallel processing systems. So what these systems do is they mimic the same table structure as databases here, and but they will have lot of storage, they will have lot of processing power, and they can run massively large data crunching jobs. So that is where this comes into picture. This is called data warehouses of the past, right? So this is how data warehouses came into picture. These were used in weather forecasting. These were used in huge grocery chains, scientific researchers, and all of these things, right? So as this one. So who created these MPPs? There were few companies like Oracle and other companies which are defunct now, but they created this. They had licensing structure. They had maintenance costs. They had engineers on site, because everything at that time happened on premise. Meaning, if you want a data warehouse, you had to buy the hardware of the servers plus software plus licenses for the software, and everything you have to install on your premise, in your office premise, right? And there had to be a data center technicians or designers, networking people working round the clock. So this was the model basically for old school data systems like data warehouses and basically MPPs. MPPs, are basically like query, you can say query engines. When we have to draw parallels, with our current era. So this was a huge burden, and not a lot of companies did that. But something really funny happened in early 2000s. You know, there was some technology called internet. Okay, that happened. So when internet happened, right? In the US, it grew around 2,500% every year, which means the amount of data generated each year has exponentially increased, not linearly, but exponentially increased, not linearly. This is linear graph, right? Like, okay, today, this is at, 10 terabyte, tomorrow it will be at, 11 terabyte, something like that. No, it's not like that. Today it is 5 terabyte, tomorrow it is 50 terabyte, like that. So the data grew massively, the data sizes, because everybody wanted to register their sites on online, be it pizza delivery, be it like mom and pop stores, be it photo uploading sites, be it video uploading sites, be it social networks, be it banking systems. Everything came onto internet right now. Around this time, there was a small startup called Google happened. Okay, what Google did? Google was founded by two PhD candidates. Okay, two PhDs called Sergey Brin and Larry Page, right? So they started to as part of their PhD project, they wanted to index the whole internet. Index meaning like, so okay, Flipkart, right? Flipkart. I want to say this as shopping or e-com. Okay, this site is that, right? Amazon, same thing. Okay, let's say LinkedIn. Okay, social networking. So when you search on any search engine, let's say shopping, I want to provide these two results. This is basically a very generalized, crude way of saying indexing. So Google wanted to do that because that was a PhD project for Sergey Brin and Larry Page, right? The indexing the whole internet into a search engine. They created something called as PageRank algorithm, and okay, they wanted to have data, all the websites data on the internet. Those days it was not even that scale, like maybe couple of million or tens of million websites and then done, right? That's it. To even process that data, they started using RDBMS systems. First of all, I told you, right? Like they, we have to have, hardware, we have to have software, and the license cost itself was very, very, very pricey. Like one Oracle server, like even to increase one core in an Oracle server used to cost in millions of dollars. It still costs millions of dollars. And first of all, RDBMS systems are not capable of, handling every type of data. Okay, they tried it. They really tried it. Google, in their earlier era, when they started, like indexing web pages, they really tried, using RDBMS systems. So why is this important? Because every time when we like process data or store data, right? We use databases. We use relational database systems like MySQL, PostgreSQL, PostgreSQL, Aurora. Uh, there are hundreds of relational databases that we still use today, and they perform really well, but not to the use case that Google wanted to do. That is like index the internet's websites on their using the PageRank algorithm. Why? Because internet contains HTML web pages, CSS for styling, and JavaScript, okay, for functioning, plus images, videos, and other text data, right? So which is in again JSON or um, you know this one, XML formats, right? So why is this important to store all of this data? Because when you want to like index the websites on their keywords, right? We have to download the contents of that website. And let's say somebody searches for some guy holding a like an object, and I want to find that guy. Seen him on some website, I want to see it. So Google has to download the contents of all of the all the contents of the website, understand it, process it, and then when somebody searches it, they has to serve the data within milliseconds. Every time you search the Google website, right, it just takes less than a millisecond to retrieve millions of results. Okay, not one result, one page of results, like millions of results. So that's how it is. That's how we see Google, right? So when Google tried to solve this with relational databases, right, the relational databases are not efficient at storing all these kinds of disparate data, and they fell short. That's why in the early 2000s, around in 2008, Google released couple of, I think around 2004, Google has Google was founded, and by 2008 they released some white papers called Hadoop MapReduce, and later they released some paper called Google Storage System, which is again called as HDFS. Right? What are these? I'll tell you in a minute. Google File System. Any doubts till now, or you want to stop me for anything? Am I good to go? Okay, somebody talk.
Yeah, yeah.
I'm not able to hear you guys. Sorry if somebody is talking. Am I? Yeah. Okay. Okay. So now let me continue on with what we were discussing. Why relational databases are not good, and why Google had to do this in new systems. First of all, we discussed about cost and this one. Now we will discuss about some other aspect called flexibility of a system, right? So since Google wanted to store all of this disparate amounts of data, like different kinds of data, and they had to like index faster. As soon as a website is published, they want to crawl the whole internet, and then they want to index that, right? So to do that, they don't RDBMS is good for storing tabular data, like let's say, like orders data, or purchase data, or some like where we can store data in record form. This is good for RDBMS. This is good for RDBMS, right? Or SQL based databases. This is good for them. But JSON or HTML or videos or images doesn't fit into this one. Doesn't fit into this format at all. Right? They don't scale well. Even if you try to put them, they don't scale well. Like if you run a query, they will just eventually crash. How can you query images? You can query the metadata of the image, like when it was taken, who it was taken, and all of that. That's it. But you cannot just retrieve the data using SQL on image data or even video data, right? So Google came up with a clever solution called, HDFS. This is a distributed, storage. Basically, we will have one master and we will have, worker nodes basically. So what this will do is it will bring the video, audio, text data, whatever, even our, tabular data, and then, break it into chunks, and then, store these chunks in, like, duplicate chunks in all of these nodes so that even if one node goes down, it will be there. That is the first thing that Google did. Okay. And they said, we will create a new paradigm called MapReduce. That means when you, okay, even before going there, why we want MapReduce, why we want this kind of structure is basically we cannot fit all the internet's data, okay, all the websites on the internet in one single machine, okay, in one single database or one single storage system. It is too large. Okay, even if you want to store in different databases, right, or different storage systems, we cannot process them easily, or we cannot just process them as one single entity. Like let's say you have 10 different places where you have opened your like stored your data, different storage servers. How do you know a job when you triggered here and here completed properly without errors and with full completion without any data corruption or something like that? You have to write a new software on top of it and coordinate accordingly. What if the data half stored here and half stored here? It doesn't make any sense, right? How would these two machines communicate between them? So this is a bottleneck for storing data, which is huge than a single machine, right? Internet's data is no joke. Even in that day, it was no joke. So Google had to come up with something called as Hadoop file system, that is HDFS, right? Where you can store data. If you want more storage, you can just add data. That's it. Okay. And you'll have more storage here. And you can store any type of data, video, audio, text, and whatever, right? And how do you process this? This is where MapReduce comes into picture. Earlier, what happened was, let's say I have a database here, right? If I want to store the data and query the data, right? This database server, this database used to be in a like will be deployed in a server, and my program or my SQL script will load the data from this database to my RAM within the same machine. Okay, within the same machine, and then it will say, okay, uh, it will load my program and it will load the data into the same RAM, and then it will process it. This will not be possible here because the data itself is spanned across multiple machines. So Google literally implemented a new programming paradigm where instead of you sending the data into RAM, I will send the program to each of these nodes, and then these nodes will locally process data here. This is called as MapReduce basically. So this is a new programming paradigm altogether. So Google came up with this one because they had the need to literally crunch the internet's data. Same thing happened with Amazon because they were the shopping website for the whole world, right? Amazon.com. It's everywhere, right? So they had to solve this problem as well. Facebook, they are the social network of the world. They had similar problems, right? Netflix, they are the movie theater for the whole world, right? So all of these guys are literally crunching petabytes and petabytes of data every single day, and they need a reliable storage system, and which is highly scalable, as well as without any licensing and all of that. If those companies have hardware, they can just run it. So this is where the Hadoop ecosystem, the open source version of Hadoop ecosystem, came into picture. Google released white papers on MapReduce, HDFS, and later the community from companies like Yahoo and other internet companies, they created this one Yarn. Facebook created Hive, Pig, etc. And then some people, uh, some PhD students again in UC Berkeley created Apache Spark, and these people are the ones that created Databricks. Databricks is the company that is founded by PhD candidates in UC Berkeley who created Spark. Databricks is again like this one. So after 2000, 2000s era, beginning of 2010s, when Amazon, did the cloud or AWS in 2008, everybody started to move their, data into cloud, because cloud is reliable. It can be, like you are basically like you can increase the compute capacity or decrease it, or just scale down to zero. You will just pay for what you use. All of that benefits occur, and you can just rent the hardware on cloud, and then you can just install any software you want. So in 2000s, that's where the AWS Redshift, after that, Databricks, Snowflake, all of these proprietary or commercial open source, basically open source projects, come like distributed as a commercial option to companies or enterprises want. So Databricks is one of the example. Redshift is other. Snowflake and BigQuery are proprietary, and ClickHouse is again a commercial open source open operating system, where you can literally see the code of the source code of these query engines or data warehouses, and you can, if you want to contribute, you can contribute to it. If not, you are just free, you're, free to use. Basically, you will be charged with the usage of how much you are using the data. So that's how these systems have evolved. So why do we need to know about all of this, right? Anybody? Anyone? Um, anyone? Why do we need to Um, okay. So anytime you use Databricks, right, you are using a Hadoop cluster behind the scenes, very optimized one. And most of the companies that we see either on Databricks or some form of a Hadoop ecosystem. Right now, Snowflake and BigQuery is also, even ClickHouse is also catching up. But the concepts that you use, like understanding MapReduce, understanding HDFS, understanding Hive, Yarn, all of these, even Spark, right? Can your knowledge is transferable to any other warehouses that you are seeing here? They are not same, they are very much different from each other, but you will be able to understand what's going on very, 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 very quickly. Even the architectures, how they do it, how you get charged, all of this, right? So any questions here, you can just put it on the chat. I'll be able to do it at the end of the session. We will just have a chat for 5 minutes. Okay. Now, why open source big tools? As I've explained, there is other benefit as well, not just the cost of software or maintenance or licensing. Speed of innovation. If let's say you want to have some changes in like your databases, or some bug in the database, or data storage system, or some part in your infra, even if to raise a complaint or even to raise an issue on the vendor side will take days to react. But if there is some issue on an open source project, somebody can take a look and just raise it. They don't have to fix it, they can raise it, and people will take notice of it. That's how open source projects work, by the way. Nobody asks anyone to work. They work out of their free time, out of out of passion and all of that. So an army of developers, developing one software, testing it, and then uh, and make it battle hardened and can be used across multiple different purposes, will make a system very robust than just closed source proprietary software. Proprietary software is not bad, but open source software triumphs in terms of speed and in terms of flexibility. They will be used in very different problem spaces compared to a normal uh, like closed source software. That's the main advantage. And even some crazy guy in an open source project can say, okay, let me run a 10,000 node cluster and check it whether it will work or not, right? So you cannot do that with commercial tools or proprietary tools. And even let's say you have bought a this one data warehouse from a vendor which is a like completely proprietary one. You don't know what's going on inside. All you do is just query and get the data. So if you want to move away from them, they will charge a bomb that is called as vendor lock-in, basically. If you want to move the data from, let's say, AWS, right? They will charge you around I think $100 per GB if you want to move like something like very like ridiculously high price. Like you cannot even imagine the cost of it if you want to move data away from AWS, right? This is how they will charge you. So to avoid all of these issues, right, we choose open source based big data tools, because even if somebody like Databricks shut shop tomorrow, I can use for the most part open source Apache Spark, and then I can just go ahead and say, okay, I'm good, I'm good here, or any other open source tool that can talk to these open source tools, right? So that's how it is. Now, coming back to the original discussion as to why we need a data warehouse. Anybody can just glance this. If you can understand my handwriting, read through it, and then you can answer the question. I'll give you a minute. Okay. So let me put forth a case here. So when we are saying something like a database and a warehouse, right? Essentially, what we are doing is we are copying the same data in a database and then putting it into a data warehouse. Why do you need two copies here? Why data duplication? Why do you need it? Right? Why do you need data duplication? Because you can run the same SQL query. Because if it is an RDBMS system, the same SQL query runs here as well as here. There is no difference. Even if you do select star from so and so table here and here, if the both the same tables have the same data, they will give you same result. There is no change at all. Why? Why do we need data duplication here? Why do we need to copy data from a DB to a data warehouse?
Keeping
First of all,
history of records.
sorry.
Keeping history of records.
Yeah, that is fine. You can keep the records history in DB as well, right?
Yes.
Okay. Why?
Backup like kind of thing, like if our main DB gets.
Okay. Yeah, I will create a read replica here, which will read and it will keep a backup here, which is again a DB. Why do you need it?
Because we store the data for analysis purpose, we cannot like edit or update anything to here. So
Okay.
that's why
Okay.
we store in
Right,
warehouse.
right, right. You have a point. It is correct, but it is not complete. you
Like
you you you
whatever
have
the transaction data will comes,
Hmm.
that will comes under the
Hmm.
database. So there we can do the modification and
Hmm.
revision, whatever the
Yeah.
update request that we can do there.
Yeah.
So we cannot do that in Dataverse, right?
We can do
Like
it, but it takes a lot of like effort and resources to do it.
okay, okay.
We can do it. We can do it. There is no one stopping us,
Oh, okay.
right? I can run the same query, like select star from here and here. I can run the delete query as well. I can run the update. I can run the merge,
Yes, yes, yes.
right? Same SQL, right? Both of them work on similar flavors of SQL. Why? Why do we need it? Think about it. It's very important question actually. In not interview sense, but your fundamental
Yeah,
understanding. Hmm.
but here we are storing huge amount of data. So in future,
Okay.
like it's
Yeah,
going
that's
to
what I'm
be,
saying, right? Instead of, like, let's say I have, 1 TB of, storage here. I'll
yeah,
say, tomorrow I'll upgrade to 10 TB. I can store huge amount of data. 10 TB data in relational database tables is not a joke. Like, it's a massive amount of data.
yes.
Like, I can literally store every single, compressed version of every single website on the whole internet in 10 TB of in a relational database right now.
Yeah,
That's how massive this, 10 TB data means.
yeah. Like going forward, we are going to like create the visualization based on this data. So it's
Okay.
very easy to create
Hmm.
the dashboards for
Right. Now
yeah
you are
this
getting there. Now you are getting there.
yeah,
Okay,
and we
got
are
it.
going to create the data marts based on this.
Right, right. Now you are getting there. Okay.
Uh,
So let me put it in a simpler and more like uh, you know uh, more understandable way, consumable way. Basically, when you if you go to a Flipkart, right, and say I want to order this product. Okay, you have paid your product, and let's say Flipkart puts you on a waiting for 1 minute. Okay, because the database needs to update. Okay, if that's the reason that they are giving, do you accept that? Or any user accepts that kind of a delay? I'll say it's just a minute. Why don't you, like, I have a database here. Okay, and my data is coming from my website, and
okay.
then to update the record in my DB, I need 1 minute. Do you accept that? Anyone?
Yes, so we can update.
Come on, guys.
Yes, we can update.
Okay. So the whole point of going to a website and ordering it is to save time and to get quick feedback as to what happened, right? The origins of internet made everyone in the country to access same resources at the same time, and we need lot of throughput. That means millions of people accessing our website, like say for Big Billion Day or Great Indian Festival, something like that, right? And then placing their orders. You want your databases to, like, do the CRUD operations, basically create an order, order record in the order table, and then pass that message saying that okay, your order is placed as quickly as possible. But for millions of people, every single user will have very small amount of data. That means just one order per user, right? One order per user. Okay, but it happens for millions of customers, right? So for these millions of customers, I need to, like, respond as quickly as possible in sub-millisecond latency, basically. So these kind of systems are called as OLTP systems or operational systems. Okay. I cannot run any analysis on top of this data while millions of customers are hitting on my database. I cannot ask this, DBs, you know, I cannot ask this DB to say, okay, you are doing a million transactions now. Can you tell me what is the most hot product that is going, that is getting most of the orders from which location? How much are they paying? You cannot ask this because your database will go down if you run that kind of a complex analysis, right? If your scale is much less, like maybe some 10,000 users are, accessing it, that is fine. You can, run analysis on, while the operations are carrying out and fine. Right. So that is, that is acceptable to some point. But if your data is complex, your data model is complex, the amount of data you are collecting is really huge, and the transactions per second is, that you have to deliver is the SLA guarantees that you deliver. These database folks, deliver to the, to the PMs or, to the leadership, saying that okay, we can accommodate, 10 million users at one, every minute of the, throughout the big billion day. If they gave that kind of assurance, right? They cannot run any analysis queries on this. These are called OLTP systems, or online transaction processing systems, right? They process transactions. What are transactions? These are small updates for, maybe couple of records, right? Or one single record that should happen very quickly. That is the nature of the systems. Okay, even though both of these, systems like, your database and data warehouse run on the same SQL query, the nature of that particular system changes. That is why we don't run analysis queries here. We don't run, smaller updates like one record, two record updates on a data warehouse. Both are wrong. Okay, am I clear on this? Guys, somebody need to give me some feedback. Yes, just give a thumbs up. You can react.
Yeah.
Okay, everybody, this is a quiet group. Okay. So now, so databases, okay, APIs, all of these are operational systems, SaaS apps, software as service apps. All of these are, your, operational systems. You cannot mess with them. You cannot run analysis queries or complex queries or, data intensive queries on these ones. No, these are not made for that. These are to facilitate lots and lots and lots of transactions from the real-time users, and, to entertain them, to entertain the user requests. That's it. So that is why we have DBs, SaaS applications, APIs, and all of this stuff, right? So the basically we will provide, do a lot of CRUD operations. CRUD means create, read, update, delete operations by lots of users, with very small data and very quick actions, right? So these are generally a single node machines. Okay, an API server will be a single node server to a lot of, it can serve a lot of traffic. Same with databases, right? Same with SaaS. SaaS, you will not, get to choose. You will just use whatever it is given to you. Generally, it will be a one single tenant for you, right? And if you want to increase the throughput of the systems, right? Like, instead of, 1 million, 1 million requests per second. Okay, requests per second. Okay, tomorrow in the big billion day, I want to have 10 million requests per second for the same database. Okay, requests per second, right? So if let's say I have 64 CPU cores for my database and 128 GB of RAM and 10 terabyte SSD, I will increase the specifications of the system, right? And I'll just double this. This is how these things will work. So now I can increase the throughput. Will it always be the case when my specs are specifications, are made 2x, right? See a 2x increase. Will my performance, see 2x increase? Will my performance also see a 2x increase? Highly unlikely after a point, right? So, instead of, 128 cores of CPUs, if I say tomorrow I have, I need 256 CPU cores, my like um, my performance might increase, like order of, 1.2x, because we will see a law, there is something called a law of diminishing returns that happens here. We will not see, like, we will not get much output or much throughput just because we increased, the specs, or we increased all of this. The throughput, depends on the data model of the data, how we are storing the data, like how we are, processing the requests, how long, we are, like, processing we are taking to process the transactions, and all of this. Not just the pure specs. Even if you do it, it has an upper ceiling, right? It can only, increase the performance up to a certain level, right? So that's why we don't want to store all of the operational data into a database. Okay, we can store, if your system is like very, very busy, maybe a year or 6 months of data for tables that get updated like a million times in a second, right? 6 months data for that table is like really, really, really huge, right? So on top of it, you cannot do any analysis. So what good it is to, like, have a database, that cannot run any analysis queries. That's where our OLAP systems comes into picture. These are, comparatively slower in transactions, right? They cannot perform, small updates. Small updates is not the, sorry, UPDATES. Small updates are not, the strong point or, advantage for these OLAP systems. OLAP basically means online analytics processing systems. This is online transaction processing systems. This is online analytical processing. Basically, what you want to do is, let's say I want to create year-on-year reports, marketing attribution. That means, okay, I've done a campaign and I want to, like, turn it into, let's see, which campaign, made a sale. Based on which campaign we made a sale, and, forecasting results, like, let's say we have got X amount of revenue, next year it will be Y amount of revenue, whether it is increased, decreased, why it is increased or decreased, all of this. So these are very huge, complex, problems to solve, or, like, answer, and they require lots and lots of data coming in from different departments, in different tables, across, different formats, like, lots of tribal knowledge on how this data is, and all of that, right? So to process all of this data, we need lots of storage, first of all, processing capacity. At the same time, people don't expect these systems to update in sub-millisecond latency. They expect it to run for half an hour or 1 hour, and then, give the results. That's how the expectations is, right? So in the OLAP systems, we see horizontal scaling. This is basically called a vertical scaling, where we are increasing the amount of, resources here to get the performance out of the system, along with other factors, right? In here, in the horizontal scaling, since the data itself doesn't fit into one single machine, there is no point in, horizontally, like, vertically increasing the data. So what we want to do is, we want to, like, split our, entire data into chunks, and, store it in different machines. So this is called horizontal scaling. Basically, instead of increasing the specs, we are increasing the number of machines here, like how it is, right? So this is how these systems work. So we will take the same, like 64 GB, 64 cores, 128 GB RAM, and 10 terabyte, to a master node which maintains these worker nodes. And then we will say, okay, I want exact same specification to all the nodes. So whenever I want a new node, I'll just, go say, okay, I want a, similar specs copy here, and then that's it. That's how we scale. Like, it increases processing power, it increases the storage as well. So these are, this principle, this is how Hadoop based systems, or even Databricks, okay, Databricks, scale in principle, or even any data warehouse for that matter. They scale, using this kind of an architecture, basically. We will discuss about all of this in much, like, depth, and, at length, in the coming sessions, but yeah. Okay, any doubts? We will end the session after discussing why we need data engineering, and we will continue maybe tomorrow or the day after on rest of the topics. I have some good things lining up, so I'll just like do it later on. Any doubts so far?
No, no, man.
Okay, this is a very safe space, by the way. Safe space meaning like you can ask any dumb question. You can ask, what does that term mean, or you have used something, and what does that mean? Nobody should be judging here, or I don't care. Like if somebody, unless somebody makes fun of, any other one, about it, like like I don't care. Like, I don't care. I'll kick them out if they make any fun of it. But yeah, apart from that, I don't care if you ask any question, right?
Like
It doesn't matter. Just ask it.
construction wise, which will be cheaper, like OLTP or OLAP?
No, that's not the right question here. That's not the right question.
Because if you have some small amount of data, maybe
Okay,
2
then
million.
yeah. Then
So,
normal DB would suffice.
we don't require OLAP, right? For small amount of data, we can manage in
Yeah, of
OLTPs
course, of
also.
course. See, even for 100,000 records, right? You can do it in an Excel sheet. You don't even
Uh,
need a database for that matter.
then
Okay,
like some small companies, why they usually go for this OLAP systems if they have very like minimum data?
see, the thing is that uh, there are lots of things here. One is like vendor marketing, like these Databricks and Snowflake and all Redshift, all these guys, right? They have salespeople that have a lot of quotas,
Yeah, okay.
and they will like target any and every company. Okay, so we will give like credits in cloud, and you can use the system, you can check for yourself and whatnot. So that's how they get locked in. They don't need it actually. Even if you have, around like, 2 to 5 million records, right? You can
Yeah.
use something like, pandas or
Some,
polars.
yeah.
Yeah, yeah, on it. And then, you're good. You're good. Polars
Oh,
can actually go for at least, 100 GB of data on your laptop. Okay. On single laptop, like normal spec laptop, 16 GB of RAM, and, normal Intel i5 or i7, laptop. Even older generation laptop. That's how good Polars is. You don't need a data warehouse. We will discuss all about these trade-offs later on, but yeah, you have a very good point actually. We don't need all of this. If and that's what I said, right? If you have smaller amount of data that is not updating frequently and you want to generate reports or run an analysis queries, right? You just straight away run from your database. But if you have large data systems and tons of records and a lot of data enrichment that is happening, like you are joining tens of different tables for under one process, like that you have 10 different processes for 10 different departments or 10 different teams, then you might need to look into something like a data warehouse.
yeah. Got it.
Did I make it like did I make it sound
No. No. Yeah,
good?
I understand. Yeah. I got it.
Okay, awesome. Yeah. Any other questions? This is turning out to be a good session, guys. Like really, I'm appreciating your questions. You guys are really like going for the meat of the discussion, not kidding around. So this is really good. I'm really enjoying it. Okay, any questions? Okay, I'll take that as a no. So we will stretch for another 10 minutes, and I'll explain, what is a typical data engineering pipeline. And then, we can sit for maybe 5 or 10 minutes more, and then, like start discussing. I'll stop the recording and we can start discussing, right? So what is a data engineering pipeline? So why do we call it as a pipeline? Okay. So even before, something like, data engineering and all of that, right? This is called at least this was called as ELT or ETL. ELT, right? ELT, ETL means basically extract, transform, load. Okay. Same thing, extract, load, transform. That's it. Just there is some difference in the principle as to why we do a transform here and then load there, but and a load here and the transform there. Yeah, yeah. We will discuss that. But basically, this is what it is. We are extracting the data from sources like whatever I mentioned here. These are also sources. Okay. And we extract the data into our data warehouse, into our raw layer, and then we load it into we transform and load it into cleaned tables, and then we aggregate the data, we make enriched data sets, and then we serve them to multiple different purposes. This is very simple, normal one. Why do we call it as a pipeline? Anyone? Why do we have to use a word pipeline?
Oh, yeah,
Why?
like means in this system, we are extracting the data from multiple systems,
Okay.
multiple storage or
Hmm.
like
Hmm.
multiple transaction system like JSON
Okay.
or any databases. So
Okay.
that we have to it will be on based on the client requirement. So based on that, we are going to create the pipelines and
Okay.
loading the
No. I'm trying to ask you, why do we have to name it as pipeline? I
One
understand,
step is
you're
one step.
so
We are giving the output of one step to the next step. So next step is taking the input from the previous step.
okay, we can call it as stages, right?
Yeah.
Why do we need to call it as a pipeline? Simple question.
but a different table have a different like
Hmm.
client requirements.
No, that is fine. Like wherever you are pointing the direction, right? That is correct, but it is not complete. So what happens in a pipeline basically,
Data
right?
cleansing, yeah,
You put something here and then you get something out here.
okay,
There can be different stages here, but the idea here is to get whatever good or data or anything, right? To go through certain stages here,
yes, correct,
right? This is why it is called as a pipeline.
okay,
And we have to do it reliably. There should not be no leaks. There should not be no breakages. Nothing. We have to do it reliably every single time in a set fashion.
okay.
Okay. This is why it is called as a pipeline. Simple explanation. Nothing fancy. Right. Now, so as data engineers, why do we need data engineering? Anybody. Just throw your answers out. I don't care. Why do we need data engineering team in the first place or ETL operations?
Because there is a massive data, lots of data, and we need
Okay.
to find out some meaningful information to make some
Exactly.
decisions. So
Okay.
that's why the data engineering comes into the picture.
Okay. But I can, like I am from sales team. I can do it my own, right? Why do I
I
need
don't,
data engineering team?
because the data is not in the way we want in that format. Sometimes we are taking a data from the XML.
I will hire some, database guy and ask him to, do it. Or software engineer, I can do it. He can do it, right? I'll hire them.
Yes.
Yes, you are doing good. You are doing good. It's just that I'm trying to go into the depth of it. That's why I'm cross questioning. Why do we need data engineering team?
Yeah, here we have different stages, right? So initially we
Forget
like
about stages. I'm
okay,
asking, why do we need data engineering team? Forget about technology, forget about stages, pipelines,
Hey, Mani.
everything. Why do we
Yeah,
need data engineering team in a
hey, Mani,
company?
so
Hmm.
data is going to be big each and every day. Like, uh,
Okay.
so data is not going to come down anyhow. So in the meanwhile, having a team with the multiple skills that definitely not gonna break anyhow in upcoming days.
No, that is like data management aspect.
Yes.
Okay. You are explaining about that, which is fine. Like, yes, we need a dedicated team to handle it. Is it the only purpose?
Money to make the raw data, reliable and accessible, like so that we can make analyze and
Yes.
make it like and for the decision making we can.
Okay. Okay. I belong to a sales team. You might be belonging to a finance team. Manikanda here, the other Manikanda here can be belonging to some marketing team, right?
Mhm.
So
Okay.
we all can do the same thing, right? We all can, like hire a software engineer and do like ETL, in our own way, right?
Okay.
Why do we need a centralized data team? Sorry, I should have put centralized or data engineering team, like centralized data engineering team in a company.
Like basically, we need to load the source data to target. We collect the data and integrate, and do the cleansing and do
Yeah,
the
that's what I'm
transformation.
saying, right? We can just do it within the teams.
Yeah, so it whole things it comes under data engineering, I thought.
Yeah. I'm not saying it is not that.
Yeah.
The reason why we do a centralized data team is that, let's say I come from marketing team, you come from sales team, Pramod comes from engineering team, right? So if we all started doing our own work in our own way, in our own, idiosyncrasies and all of that, there will be a lot of tribal knowledge. That means nobody knows exactly what is happening across the teams. Even if they want to communicate it well, people will not take it the correct way what the intended audience do, and then it starts the whole politics of it, and like finger pointing and all of that. It will quickly become a cultural issue rather than a technical capability issue. Okay, so to address all of it and to make the data reliably go to each and every single consumer that wants to consume any data with uh, like correct permissions and correct accesses to the data, we establish a standard called data engineering team. I can extract marketing data, I can extract sales data, I can extract product data, I can extract transactions data, every single data, and I can process it reliably with one standard, because every data processing request should come to one team, and they are responsible for serving the data across every single member, be it for as I mentioned here, be it for BI dashboards, reporting, machine learning, data serving with APIs, whatever, right? So this has to happen reliably, and there should be one single source of truth, reliable source of truth. That is why we need a data engineering team. Am I clear?
Yeah, okay, Manish, got it.
Yeah. If not, what happens is tomorrow sales comes and says, okay, we made $10 million of sales this time. And marketing comes and says, no, you haven't done that. You're duplicating your data. What's going on? And then product comes and says, there are no 10 million, things to like serve. How you guys came up with that number? So what happens in the boardroom now? CEO will be looking at everybody's face, and he'll be like, literally like face swapping himself and saying, okay, oh my God, what have I done? There is an issue here. We are not getting reliable data. All of these are morons who cannot, handle the data properly or get me the details that I want. Right. So this quickly becomes a cultural issue. To avoid all of that, data engineering is born. There is another, version to this story. Basically, when machine learning took off, right, everybody started to, think that okay, they will build the best of the best models and whatnot. And to their credit, they built it. But later, they realized that without good data, the best model, just is a dummy. It's like a car without an engine, basically. So they become data engineers for the fact that they see it as a problem to reliably get the data, process it, and then serve it to machine learning teams or BI reporting or whatever. Right? So this is another part of the story. This is a true story. There are at least, in my career, I've seen hundreds of, data scientists. They have moved to data engineering because data engineers are like, handling the data end of the day. So that's how it is. That's why we need data engineering.
Okay.
So yeah, that's how it is. Let me pause here and we will talk about the future and, data engineering skill set tomorrow. And, around the same time, I'll schedule another session again. But yeah, this is what it is. Any doubts? This has been a great session, guys. Thank you so much for, coming up today. Yeah, let me, just stop this recording. We will just have a chit chat. How can I turn off?